Oh, shoot! Welcome to Calculus A, taught by graduating class of 2013, Calculus BC. Today we'll cover the fundamental theorem of calculus, chapter 4, section 4.
The fundamental theorem of calculus is true, assuming that f is continuous on the closed interval ab, and capital F is the antiderivative of the function f. The integral of the function from a to b is equal to the antiderivative of that function of b minus the antiderivative of that function at a.
Example problem. Use the fundamental theorem of calculus to find the definite integral of this function. First, you find the antiderivative of the function using the methods that you learned in the previous chapters. You apply the fundamental theorem of calculus by plugging in 7 to the antiderivative. Now you plug in 1 to the antiderivative and subtract it from the antiderivative at 7. Now you use algebra to subtract the antiderivatives to find the final answer. And now we come up with an answer of 630.
Now, using the fundamental theorem of calculus, we can solve the same problem using a different method. You set it up by finding the antiderivative in the same way. However, when you plug in the bounds, you do it differently. When you plug in the bounds to the x's, you can take the constant and put it in front of the x and plug each constant in to the power that the x is to and subtract them from each other. For example, 5/3 x cubed becomes 5/3 times 7 cubed minus 1 cubed, and it's the same for each one. Then you simplify the answer and you end up coming to the final answer of 630 as well. The mean value theorem for integrals can be found using the mean value theorem, a concept you learned in a previous chapter. This is the mean value theorem for integrals in a different form. If you notice, each function in the mean value theorem for integrals is an integral of one of the functions in the mean value theorem. If you times each side by b minus a, you come up with the standard form for the mean value theorem for integrals. By applying the fundamental theorem of calculus, we determine that the integral from a to b of the function is equal to the f of some c in the interval ab times b minus a. Remember, the mean value theorem for integrals is only valid if f is continuous and c is some value on the closed interval ab.
Find the average value of the given function on an interval -1 to 2. Using the mean value theorem for integrals, you simply plug in a, b, and f of x. You solve the definite integral using the fundamental theorem of calculus. Finally, you simplify the problem to come out with a final answer of 8.
Now to learn the second fundamental theorem of calculus. This theorem is valid only if f is continuous on the interval I, which contains the point a. The derivative with regards to x of the integral from a to x of f of t dt equals f of x times x prime. In this equation, x is the variable and a is a constant.
This is an example problem using the second fundamental theorem of calculus. We're allowed to solve this integral by plugging in x everywhere there's a t. We could explain why this is allowed, but you don't really need to know it for the AP exam, simply that you do plug in x everywhere you see a t. Here we are working the same problem, except we replaced x with x squared. So now we plug in an x squared everywhere there's a t. Now, as you know from the chain rule, we have to multiply everything by dx, which is in this case 2x, to everywhere we plugged in an x squared.
The net change theorem is a manipulation of the fundamental theorem of calculus, which allows you to find the net change from a to b of a function on the interval a to b. Example problem. Given that the f of 0 is 20 and the integral from 0 to 6 of f of x is 30, find f of 6. The net change theorem can be rearranged to find f of b. Now, given the values can be plugged in to find f of b, which is 50.
The fundamental theorem of calculus is awesome.
The fundamental theorem of calculus?
Now complete the formative assessment and check your answers to the answer key, and decide if you agree with Mr. Bordell or Mr. Ennis.